Welcome back, ladies and gentlemen. In this video, we are going to discuss the opening topic of ellipses today. All right. But before we do so, I want to kind of show the relationship between circles and ellipses. So the main goal of this video is to identify the anatomy, if you will, of the ellipse, and then identify its kind of standard equation for an ellipse. Before we get there, I have a question. How would you define a circle? How would you define a circle? Think about it. How would you define a circle? Well, a circle, if you think about it, has a center, of course. And how would you define what makes a circle a circle? Don't just say a rounded figure, because as you'll see, an ellipse is a rounded figure. So what makes a circle specifically a circle? Well, if you imagine that from a fixed point, C, I could have a distance that goes out here. We'll call it A. A distance that goes out here, also 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 A. And so on and so forth. And all of those exact same distances would help us create our circle. So you could say that it's the set of all points that are equidistant to a fixed point. Well, where does that kind of differ for an ellipse? Well, an ellipse is the set of all points whose distances from two fixed points have a common or a constant sum. A constant sum. Okay. So, before we go into the rest of the definition, let's talk about the anatomy of an ellipse. And I am going to start off with an ellipse that is horizontally represented. Okay, so similarly, we have our center. We still are going to have that at h comma k. To the right and to the left, there's an equal distance that has 2 points that we are going to call the focus. That should sound familiar from our parabola discussion. Now those guys are our focus, and plural, together, they are our foci. To the right and to the left of the focus, there are 2 additional points. We denote them with V's because those are our vertex points. Those are our vertex points. All of these points that I just drew right now lie on a line called the major axis, if it is horizontally represented, okay? If it's horizontally represented. Well, then vertically represented from the center, there are 2 other points on the same line as the center vertically. And they don't really have a denotation, any kind of notation or anything kind of like that. But they are the minor axis endpoints. So this guy would be our minor axis. And these 2 axes and these sets of points allow us to create our ellipse. Okay, so some other important information about the anatomy of an ellipse. There are some important distances. There is an important distance from the center to either of the focus, and that is denoted with a lowercase c. And there is an extremely important distance from the center to the vertex that is denoted with a lowercase a. That is super, super important there. And then finally, there is a secondary distance from the center to the minor axis endpoint that we denote with a lowercase b. And now these are all going to be important in representing the template for our ellipse equation. The last thing that I want to kind of talk about here is maybe just in case, the major axis would go from vertex to vertex. And then if you hear the term semi-major, that term semi-major is from the center to one of the vertices. Okay, so just so we know about that. All right, so what does this equation look like here? Well, we would still represent it with x minus h squared, because it's represented horizontally, plus y minus k squared. But since we don't have a radius that's equivalent all the way around, we set it equal to 1. And so in order to set it equal to 1, we would have had to divide by something in order to get a 1 on the right-hand side. So what did we end up dividing by? Well, it's different for both the horizontal and the vertical aspects of the ellipse. And so these are where these important distances come into play. The distance from the center to the vertex, lowercase a, that's going to be squared underneath the horizontal component, or the x component of it, because it's horizontally represented here. And then underneath the vertical, or the y component, is going to be the minor axis, the semi-minor length squared there. And so this is the horizontal representation. Well, okay, what happens if it is a vertical representation? Well, if it's a vertical representation, then we just switch. We have x minus h squared plus y minus k squared equals 1. Under the vertical would be the distance from center to vertex vertically, because it's going to have a vertical representation now. And then it would have b squared for the minor axis, which would then be represented from a horizontal aspect there. And so we will use some examples of these guys in our